Okay, so chapter 5, multiple degrees of freedom. Like I said, last year in level 2 dynamics, you would have been introduced to this stuff. So quite a lot of this you may have covered before, but it's useful to review it because we're going to be basing the next few chapters on multiple degrees of freedom. So it's important that you know how to do the basics. So we'll first off look at 2 degrees of freedom systems, looking at finding the equations of motion, natural frequencies of mode shapes. That stuff you've done before, certainly. General solution was to go through an example. We'll talk a little bit about semi-definite systems or degenerate systems, and talk about initial conditions, and then we'll move on to a 3 degree of freedom system down here. It follows very much the similar method that you have up here, but obviously we're moving into more than 2 degrees of freedom. So here's a typical 2 degree of freedom system. We've got 2 masses, M1 and M2. Okay, we're connected with springs, K1, K2 and K3, with dampers, C1, C2 and C3. Okay, and mass 1, we've got a motion that's given by X1, okay, and there may be a force being applied to mass 1 called F1, and the same for mass 2, you've got X2 and F2 being applied to those masses. And if we apply Newton's second law, it's quite clear that mass times acceleration is the sum of all the forces. Well, the only force that's in the same direction as x is the applied force, F1, and all the other forces, the damping forces and the spring forces, are opposing it, hence the minus signs here and here and here. Now C2, okay, is the damper that's between the 2 masses. If I go back to the picture, you can see that C2 is between the 2 masses, and we know that damping and the spring force of K2 is based upon the relative velocity for the damper and the relative displacement of the spring. And so when you've got these the equations, you can see quite clearly that instead of this just being C2 x1 dot, we've got to take the relative velocity, so x1 minus x2, x1 dot minus x2 dot, multiplied by C2. And over here we've got the same thing with the spring, okay? And so what I've done in this line is I've just rearranged it. I've put all the terms with x in, and x dot in, over onto the same side as the mass times acceleration. Okay, so all those minuses become pluses over here, okay? And I've multiplied out some of these terms. So I've grouped them in terms of x1 dot, x2 dot, and x1 and x2, okay? And then obviously f1 is on the other side. You can repeat the process for the second mass, okay? And now obviously we've got the relative velocity, but this time it's x2 dot minus x1 dot. Notice that it swaps. You start with the term that you're referring to, okay? So here we've got x1 dot minus x2 dot, because I'm dealing with x1. Here we've got x2 dot minus x1 dot, because I'm dealing with x2, okay? And so you do the same thing again, and obviously down here we've got the, we've got C3 as well, so there's a C3 term, and K2 and K3. So those are 2 equations, this one here and this one here. And what you can do is you can convert that to write that in what's known as matrix form, okay, which looks like that. And so if you multiply this matrix out, you get M1 times by x1 double dot, okay, and then plus C1 plus C2 times x1 dot minus C2 times x2 dot, and then K1 plus K2 times x1 minus K2 times x2 equals F1. That's the first equation. The second equation is basically the second one, okay? And this could be represented with this by this method, where big M in square brackets is the mass matrix. We've got C in the square brackets, which is the damping matrix, and then K in the square brackets, which is the stiffness matrix. F in curly braces is the force that's being applied. Okay, and x in curly braces, and x dot and x double dot represents the displacement, velocity, and the acceleration respectively. And this will always be the case for a linear system, okay? If your system is linear, you should be able to write it in this form, okay? Where you have a mass matrix, a damping matrix, and a stiffness matrix. If our forces are 0, then obviously it's exactly the same equation, but instead of F1 and F2, we've got 0 in there, and that makes sense. Now, this is new. You won't have covered this last year. There is a quick method that will allow you to fill up those matrices. So if I give you quite a complicated system and say, what's the equation of motion, okay, in matrix form, there's a quick method you can apply that will quickly allow you to fill up those matrices so you've got your equations of motion. You don't have to go through Newton's second law and finding mass times acceleration and applying all the forces, working out what the forces are between, say, mass 1 and mass 3 and so on. There's a quick method you can follow. And these are the rules that apply. J and I are just basically indices of the matrix. Okay, so the first box in a matrix in the upper left-hand corner would be M11, or for the mass matrix, M11. Okay, and obviously in the bottom corner would be M33 or M22 or whatever. Okay, so that's MII, and that just equals MI. So in the first box, M11, that just equals M1, the first mass. And in the second one, M22, that would just equal the second mass, and so on. Anything that's not on the diagonal, so Mij, okay, so M12 and M21 will be 0. So basically your mass matrix is just the diagonals, okay, and you simply list the masses that are in your system. Okay, M11 will be M1 and M22 will be M2. That's exactly what. And anything off diagonal, which is given by the Ij, because they're not equal to each other, will equal 0. There's the mass matrix, straightforward. Now for the damping and stiffness matrices, it's a little bit more complicated. For the diagonals, okay, so CII and KI, what you do is you take your mass and you look at all the springs that are connected to that mass. So connected to either ground or to another mass. And you add them up, okay, you sum them, okay, all the dampers that are connected to that mass, you add them up, and that will be on your diagonals. So for C11 or K11, you look at, for K11, you look at all take X1 and you look at all the springs that are connected to it and you just add them up, and that will be what's in the diagonal, okay? For the first mass, it will be K11 and the second mass will be K22. And the same for the dampers, okay? So the sum of all the springs and dampers connecting the mass to either ground or to another mass. For the off diagonals, what you do is you take the minus, okay, the sum of all the springs and dampers connecting mass I to mass J. Okay, so if we had a 2 degree of freedom system, C12 and K12 is minus the sum of the springs and dampers connecting those two masses together. If you have a 3 degree of freedom system, then obviously you've got 1, 3 and 3, 1 and 2, 3 and 3 and 2, 3 and 3, 2, and they will also be the same thing. So if I had a 3 degree of freedom system and I'm looking at the spring connecting mass 2 to mass 3, then obviously this would be K23, so second row, third column, okay? And that links mass 2 to mass 3. Is that a question? Are you stretching? Okay. So, diagonals is the sum of the springs and dampers connecting M1 to ground or to another mass, okay? And the off diagonals is minus the sum of the masses connecting the masses, it's the sum minus the sum of the springs connecting those masses together, or dampers. And that builds up your M, C and K matrices. And for a linear system, those matrices will be symmetrical, okay? Symmetrical, what we mean by a symmetrical matrix is a matrix where you can reflect it about the diagonal and you get the same thing, okay? So that's why C12 will equal C21, okay? First row, second column will equal second column, first row. So first row, second column will equal second row, first column, okay? So that's what we mean by the fact that they're symmetrical. So once you've got your equation of motion, we want to find the natural frequencies. Now, if you remember, back when we were looking at chapter 2, we had the notion of natural frequencies and damped natural frequencies. Well, obviously, to find the natural frequencies, we have to neglect damping, okay? And so we take out the C terms in that equation, and we end up with this as our equation of motion, okay? Now, to find the natural frequencies, we have to make a substitution, okay? What we do is we substitute in a solution for an oscillation, which is given by this, okay? This is one substitution we can make using cosine omega t plus phi, okay? And basically, we substitute in we know that obviously the x is the position of the thing, and that's going to have an amplitude and an oscillation of frequency omega. Okay, we don't know what omega is, and we don't know what xi is, but you'll come to find out that this amplitude doesn't actually matter. And so what we do is we make the substitution, okay, where I equals 1 or 2, okay, and obviously you take the second derivative of this with respect to time, and you get a minus omega squared come out, and you have the same term over here. And so we'll do that substitution, and if you plug them in, you end up with, you can go through the motions, you plug it in, and you can rearrange it, and you end up with this matrix times by x1 and x2, okay? And you've obviously got over here, you've got a cosine omega t term that if you divide both sides of the equation by that term, it disappears, so we don't need to worry too much about it. And the same could be said for the x1 and x2, but like I said, let's not worry too much about that. This matrix, okay, if I just go back, you can see that what happens here, we end up with x1, x2 times by minus omega squared, okay, and then times by the cosine term. And here we've just got big x1 and big x2 times by the cosine term. Like I said, the cosine term disappears, and this becomes x1 and x2, the double dots disappear. And so you end up with minus omega squared times by m1, okay, plus k1 plus k2, okay, times by x. And here we've got minus omega squared times by m2, okay, minus k2 plus k2 plus k3 times x2, okay, which is where that matrix comes from. And so once you've got this equation, assuming you've practiced it enough, you can often jump straight to the impedance matrix without having to go through the process of the substitution and stuff. If you can recognize that here we've got the minus omega squared times by m1 plus the k terms, okay, minus the k terms that relate to the second mass, x2. And this process, okay, so the stiffness minus omega squared times by the mass, this is known as the eigenvalue problem, okay? And the natural frequencies will be the eigenvalues, the mode shapes will be known as the eigenvectors, and from this equation we can find those things. So to solve the eigenvalue problem, to find the natural frequencies, okay, is what you have to do is you have to take the determinant of that matrix, okay? Now the determinant of a 2 by 2 matrix, you should know, you take the diagonals, you multiply them together, okay, and then you take these diagonals and you subtract them multiplied together, okay. So it's this times this minus this times this will be the determinant of the 2 by 2. On your formula sheet, at the back of your notes, okay, on the first page, there's a 3 by 3 determinant, and it's a solution for a 3 by 3 determinant. I'm not expecting you to remember the 3 by 3 one, because it's a bit more complicated, but the determinant of a 2 by 2 you will have to remember. Now if you take those diagonals, multiply them together, okay, so we've got the first term and the fourth term, that's the diagonals multiplied together, minus the other two multiplied together, you end up with this, if I expand it out, okay, you end up with m1, m2 times omega to the power of 4, okay, then you've got omega to the power of 2 multiplied by all this lot, okay, and then omega to the power of 0, you've got this minus this, okay. I shan't bore you with the maths, but it's quite straightforward to multiply out those terms, okay. Obviously, you know, to start off with, you take k1, you multiply k1 by this, and times this, okay. k2 multiplied by this, and this, and then minus omega m1 squared, m1 omega squared times this, okay. And you can see quite clearly that this bit times this bit will give you the first term, okay. Now if we replace, for the sake of argument, you don't have to do this, but if we replace, say that lambda equals omega squared, okay, then quite clearly this equation becomes a quadratic equation. We've got a lambda squared here, a lambda here, and a lambda to the power of 0 over here. And so there's our quadratic equation. And obviously if you've got a quadratic equation, you can solve it using the quadratic formula, okay, to find a value for lambda. And it's quite clear that lambda, there'll be two terms, okay, and each of those will relate to natural frequencies, because lambda 1 and lambda 2 will equal omega 1 squared and omega 2 squared. And you can then solve it for natural frequencies to find omega 1 and omega 2. Okay, there's two values. It's a 2 degree of freedom system. There'll be two natural frequencies. A 3 degree of freedom system will have 3 natural frequencies, and so on. A 4 degree of freedom system will have 4 natural frequencies, and on. Okay, and they'll be denoted by omega 1, omega 2, and so on. And last week when we talked about omega 1 and omega 2 with the Fourier series, they represented fundamental first harmonic. Okay, here they're not related in the same way. Okay, omega 1 and omega 2 are independent of each other, based purely on the dynamics of the system. So as we said, 2 degree of freedom system will have 2 natural frequencies, and you'll end up with 2 mode shapes. Okay, a mode shape represents the relative motion of one mass and the other mass. Okay, so essentially, if you've got, say, you've got a 2 degree of freedom system, you've got one mass that moves by 1 meter. Okay, this or 1 millimeter or whatever. The other mass will move by a certain amount based upon that whatever unit that mass is. So if it was 5 millimeters, it'd be 5 times that set amount. Okay, so it's the relative amplitudes of masses, and the way to do that is you set the amplitude of one of those masses to 1 whatever. It doesn't really matter, 1. Okay, and then you find the relative motion of the other mass relative to that one you set for 1. And so we end up, what we do is we take our equation of motion that we had. Okay, remember we had x1 and x2 over here. What I've done is I've divided both sides of the equation by x1. And so obviously that x1 divided by x1 obviously is 1. And we end up with x2 divided by x1 on the bottom down here. And what we do is we set this term to be r. And what we're doing is we're going to find r. Okay, so we set that to be r. We end up with this equation. And then what you do is you take each natural frequency that you had, omega 1, omega 2, you insert it into here, and then you solve to find r. Now what omega 1, omega 2, if you've got values for these things, you can work out specifically what those values are in terms of numerics. But if it's in terms of k and m, you can work it out. But obviously what will happen is the k's and the m's will often cancel out, so you just end up with numbers here, and you can actually work out what r is. Here I've not done that. I've just looked at I've kept it in terms of variables. Okay, so by using our found values for omega 1 and omega 2, we can insert them into this equation and solve for r. Okay, and we find 2 mode shapes, 1 and r1 and 1 and r2. So for the first mode shape, we stick an omega 1 into here. Okay, and you can take the first line of the equation, so it's this term multiplied by 1 minus this term multiplied by r. Okay, so we end up with this term plus this term equals 0. Okay, because that's on the other side. And you can rearrange solving for r1, and you find that r1 is k1 plus k2 minus m1 omega squared, so it's this term, divided by k2. So that solves for r1. You get a first mode shape. You repeat the process for r2. So you take your omega 2, you stick it into here, okay, and you go through the process solving for r2. So that's the process. We'll do an example in a minute, but just before we do that, the general solution. For a 1 degree of freedom system, so this is back in chapter 2, the general solution looked like this, yes? Okay, this is pre-oscillation, undamped. We ended up with an equation that looked like this, a simple sinusoid. Cosine omega naught t times plus phi times by an amplitude of a certain value a. Now for a 2 degree of freedom system, okay, what happens with mass 1 will affect mass 2, and the same, and vice versa. And so x1 is going to be 2 sinusoids of certain amplitude c1 and c2, okay, and at that certain frequency, omega 1, which is the frequency of the first, and the omega 2, which is the second natural frequency. So that's x1. x2, you need to multiply that by the relative amplitudes. If c1 moves by 1 millimeter in terms of amplitude, then for x2 you've got c1, which is the 1 millimeter, times by your mode shape, r1. Okay, and the same thing for c2, okay, times by r2. And so you can put that in matrix form as well. Okay, and basically you just replace x with x1 and x2. Okay, so x1 is c1 times by 1 times by cosine plus c2 times by 1 times by cosine. And obviously x2 is c1 times by r1 times by the cosine plus c2 times by r2 times by the cosine. Okay, so that gives you those two equations. Or we know that this c1 cosine omega 1t plus phi 1, you can rewrite that in terms of cosines and sines. And so we end up with this form of the equation where you've got the same vector here, okay, but then you've got that different form of the sinusoid. And as you can see, that's a bit longer because it runs off the end of the slide, but you know what that says. So as a very basic example, we've got 2 degrees of freedom, we've got 2 masses which are the same, and we've got 3 springs which are the same. There's no dampers, we don't worry about it. And we've got x1 and x2, and the question is, find the equation of motion, find the natural frequencies, and find the mode shapes. Well, it's very straightforward. The mass matrix is M and M in the diagonals and 0 everywhere else. For the stiffness matrix, okay, in the diagonals, let's take x1, okay. The first item in the diagonals will be the sum of the springs connecting mass 1, this one here, because this is x1, to ground or to another mass. So obviously quite clearly it's going to be 2k. Okay, and for the second diagonal, that's quite clearly also going to be 2k. And then for the off diagonals, so first column, second row, and second column, first row, it's going to be minus the sum of the springs connecting the masses to each other. So it's going to be minus k. And so quite clearly you can jump straight to that using the quick method. We're going to practice the quick method when we do an example. We make the substitution, okay, to end up with this form of the equation. And look, this term is multiplied by x1 and x2. This one's also x1 and x2. The cosine term can disappear. We can combine those two matrices together, and that will give us our mechanical impedance matrix. Okay, so that's the substitution we make. The other substitution you could make, okay, again referring to chapter 2, we know that cosine can be represented by the real part of an exponential, e to the j omega t, okay? And you can do that substitution, you'll get exactly the same result. It doesn't really matter which one you choose. So that line we had on the bottom gives us our mechanical impedance matrix. You take the determinant of this, okay, so you end up with this as your solution. When you multiply this term by this term, minus this term by this term, you end up with this as your equation. M squared, lambda squared, okay, plus 4, minus 4 mk lambda, plus 3k squared. What I've done is I've replaced omega squared term by lambda. And you can end up finding that, you know, if you go through the quadratic formula, you know, you should all know the quadratic formula, yes? Minus b plus minus the square root of b squared minus 4ac over 2a. Okay, you just go through that process, you end up with, we've got 1 plus or minus 1 k upon m. And so if you, 2 plus or minus 1 k upon m. And so if you go through that, you get 2 values, k upon m and 3k upon m. And obviously omega 1 will be the square root of the first term, and omega 2 will be the square root of the second term. It doesn't matter what order you do them in, okay? Just make sure you're consistent with the suffixes. Omega 1 will refer to the first mode, and omega 2 will refer to the second mode. Okay. So with the mode shapes, we replace x1 and x2 with 1 and r, okay? And then you stick in omega 1 to find r1, and you stick in omega 2 to find r2. It's quite straightforward. And so if we went through that process, for omega 1, okay, we had a m omega 1 squared. Well, if omega 1 is k upon m, then you can obviously replace that, and there you end up with k. And so we had a k, 2k here minus a k term. Obviously, what I've done is I've just divided the whole lot by k to get rid of the k's. We end up with 2 minus 1 times by the vector 1 and r1. And obviously, if you go through the process, you end up with 1 times by 1 minus r1 equals 0. So therefore, r1 must be 1. Okay, that makes sense. The masses are moving up and down together. For omega 2, so we stick in 3 k upon m for omega 2 squared. Again, the m's will cancel. We end up with 3k. I divide the whole lot by k to get rid of the k's, and we end up with minus 1 times by 1 and R2, so you end up with minus 1 times by minus 1 minus R2 equals 0, therefore R2 must be minus 1. So those are the two mode shapes. We had 1 and 1, okay, so the two masses are moving up and down together, okay, in unison. And then the second mode shape, they're moving in opposite directions, okay. When this one moves up by 1, this one will move down by 1, okay, because those are the two mode shapes. And obviously this is a very simple case where the masses are the same and the springs are the same. You've got those two natural frequencies. Often that won't be the case, okay. You'll have different masses and different spring stiffnesses, and so you won't get exactly the same sort of motion. But this very simple case, that is what will happen. And the first natural frequency will be a certain value, and this will be root 3 times that natural frequency will be the second value. And the general solution, like I said, basically is a superposition or the summation of the first mode and the second mode, okay. And so we've got, the first mass, we've got C1 times by cosine root k upon mt plus phi 1, okay, and plus C2 times by 1 times by cosine of root 3k upon t times phi 2, okay. And this, obviously with this one down here, you have to include the values that we found for r. And those terms C1, C2, phi 1 and phi 2 can be found from initial conditions. And we'll talk a bit about initial conditions in a minute. So, semi-definite systems or degenerate systems are systems that aren't connected to ground. Okay, there's a system where no inertial element or spring is connected to ground. Okay. Now, an example of a semi-definite system could be the turbine compressor. Obviously the shaft connecting the two in a jet engine. They're not connected to ground, okay? They are connected to each other. Obviously the turbine turns the compressor in a jet engine. And that shaft will have a certain element of torsional stiffness, okay? And so this could be the inertia of the compressor. You've got your shaft, and this could be the inertia of the turbine. They're not connected to ground in any way, okay? They're connected by bearings. Okay, but obviously you've got a system that there is semi-definite. But this system could be sort of floating in space. Okay, it's the same sort of thing, not connected to ground. And to solve it, you go through the same process. Okay, so again, our diagonals will be the certain masses, and here there's only one spring in the system. It's connecting the masses together, and so we've got k and k in the diagonal, and we've got minus k and minus k in the off diagonal. Okay. Again, you can make the substitution for x1 and x2, and you can go through and find our system here. This is the mechanical impedance matrix. We can find the determinant, and we get our natural frequencies. Okay. And so if we do that, you can see quite clearly that we end up with omega squared outside of the bracket with a quadratic inside it. Okay, essentially. The only way this solution works is if this is 0. Okay, so there's one solution, omega 1 squared is 0. Or if this lot is 0, so you get a second value for omega as well. 2 degrees of freedom, 2 natural frequencies, but one of those natural frequencies is 0. Okay, and that makes sense. If the system's floating in space, the two masses are just moving around together. They're not oscillating at all. Okay, there's no frequency because it's not oscillating. The other one is going to be a relationship between the masses and the stiffnesses, okay, where the masses are moving around. The thing could be moving around in space as well, but those masses are oscillating together, this frequency, dependent upon these masses. Okay. It's quite clear that if mass 2 was huge and mass 1 was not very huge, okay, what you end up with here is you end up with this number being insignificant compared to this one, so you end up with k m squared, m2, over m1, m2, the m2's cancel, you end up with k upon m, which makes sense. Mass 2 is ginormous, okay, mass 1 is just oscillating against mass 2, it's like a single degree of freedom system. Okay, so that's worth remembering. And so we substitute those values of omega back into the mechanical impedance matrix to determine the mode shapes, and we end up with two mode shapes. The first mode shape, we said, is no oscillation. And so obviously if mass 1 moves by 1, mass 2 is going to move up by 1. Okay, so you end up with 1, 1 as the first mode shape. And for the second mode shape, so there's 1, 1, okay. That's called the zeroth mode. The second mode shape, omega 1, okay, is obviously a relationship. It's going to end up being a relationship between the masses. Okay. And again, if M2 is ginormous compared to M1, this term drops to 0, and so you end up with basically mass 1 moves up by 1, M2 is not going to move at all, okay, which makes sense. It's a single degree of freedom system. So in this case, the motion of the masses is relative to each other is dependent upon their masses, okay? It's not a certain value minus 1 or plus 1 or whatever, it's dependent upon the masses. So if the masses are equal to each other, it's going to be minus 1. If they're not equal to each other, it will be dependent upon those masses. Okay. Degenerate systems, now single degree of freedom system. Now initial conditions. We saw that the general solution for a 2-degree freedom system takes this form. Okay, and what I've done here is I've replaced those cosine terms with the cosine and sine terms for the sake of argument. And with initial conditions, what you do is you take time to be 0. And obviously certain things will happen to these terms when sine and cosine, when time is 0 to the cosine and sine terms. A1, A2, B1 and B2 are determined by their initial conditions. And like I said, what you do is you define x1, x1 dot, and x2 and x2 dot when t equals 0 to be certain values. Obviously here we've defined them we've defined them to be 0, so where everything's initially at rest. Generally that won't be the case, but what we do is we take the first derivative with respect to time. So there's our solution to find x1 dot and x2 dot. And when t equals 0, so if we went back to the first, so this is when t equals 0, okay, for the displacement, cosine times by 0 is 1, sine of 0 is 0, so that disappears, as does this term. And so we end up with x1 at time equals 0 equals a1 plus a2. x2 equals r1 a1 plus r2 a2. And if you do the same thing with the derivative term, x1 when time equals 0, obviously this term now disappears. We end up with b1 omega 1 times by 1 plus b2 omega 2 times by 1 because the sine term disappears. And obviously with x2 you've got the same thing except it's multiplied by r1 and r2 as well. And so you end up with 4 equations and 4 unknowns. Okay, so you can solve it. A1 and A2. Okay, and B1 and B2 are our 4 unknowns. Everything else we should know. We know our natural frequencies and we know our values for R. And so we can solve it. And question 2 in your exercises is giving you the initial conditions and you go through and you solve for those initial conditions. Right, a 3-degree freedom system. This is merely an extension of what we did for the 2-degree freedom system. Okay, and you can extend it to n degrees of freedom. Okay. Anything beyond 3 degrees of freedom is laborious stroke impossible to solve by hand. Okay. So you don't need to worry about going through that process for anything more than 3 degrees of freedom. You know, working out the determinant of a 4x4 or 5x5 is not a simple task, and it's not something I wish to test you on, and probably not something you wish to do. Okay. So we're going to limit it to 3 degrees of freedom. And for a 3 degree of freedom system, it's the same process, but what happens is that KD, our determinant of K of the mechanical impedance matrix, end up being, instead of a quadratic, it ends up being a cubic equation. Okay, there'll be omega to the power of 6 in there, or lambda to the power of 3. Now again, that's quite difficult to solve by hand, and so what will happen? It's only solvable by hand if you've got a semi-definite 3-degree of freedom system, because you know, therefore, one of the natural frequencies will be omega squared. Okay. Sorry, will be 0. One of the natural frequencies will be 0. And so obviously you can solve that by hand, because you take out the first natural frequency, you end up with a quadratic, which you can then solve in the other way. So let's do an example. Here's my 3-degree of freedom system. Okay. I've got mass 1, mass 2, and mass 3. They're all equal to each other. I've got K1 and K2, the two springs. They're also equal to each other. And obviously I've got displacements x1, x2, and x3. It's semi-definite. It's not connected to ground with the spring or mass. Obviously it's running on ground, but we don't need to worry about that. We assume the wheels have no mass, and there's no friction, and the springs are linear. Okay. So using the quick method, we can fill up our mass matrix, MMM, down the diagonal. And obviously the stiffness matrix, you've got the same thing. Mass 1 is connected to mass 2 by K. Mass 2 is connected to mass 1 and mass 2 by 2 springs, so it's 2K. And mass 3 is connected to mass 2 by one spring. Okay, and obviously between mass 1 and mass 2, so this box and this box, we've got minus K. Between mass 2 and mass 3, this box and this box, we've got minus K. And between mass 1 and mass 3, there's nothing. So we've got 0 in there. Make the substitution, you plug them in, you get your mechanical impedance matrix. Okay, you should start to see the pattern of what goes on. We end up with, if we've got 1K and 1M over here, we've got K minus M omega squared. And obviously here it's 2K minus M omega squared and K times M omega squared. And if you remember, the mass matrix has 0 everywhere else, so these remain the same as what was in the stiffness matrix. Now, you're thinking, well, hold on a second. We've got, if we set this to be 1, we've got 2 unknowns. But the thing is, we've got actually 3 equations that we can use to solve those 2 unknowns. And so it's relatively straightforward. But we first need to find our natural frequencies. So again, following the equation in the solution, the formula sheet, you can solve a 3×3 determinant. Okay, we'll go through that in an example, and you can end up getting an equation of motion. It's quite clear that this can only be true if this is 0, or if this is 0, or if this is 0. And so we end up with 3 natural frequencies: 0, K upon M, and 3K upon M. We know by definition it's a semi-definite system, so the first mode must be 1, 1, and 1. Okay? And if you went through the process of sticking in 0 in here and solving for these 2 values, okay, when this is 1, you end up with 1, 1, and 1. And that makes sense. All 3 masses are moving around with no oscillation. When you stick in K upon M, you go through the process. Again, K upon M, the M's cancel, you end up with just K's. You can divide everything by K and you get this. Okay, we've got 3 equations. This one times by this one times by this, and this one times by this. We've only got 2 unknowns. You can solve it, and you find R2, which is the motion of the second mass in the first mode. So that's why it's R21. And the third mass in the first mode, you end up with, you can go through and solve it, and you end up with 1, 0, and minus 1. And that's the mode where the first mass doesn't move, okay, but the other 2 masses are moving in opposite directions, okay? So that's like a 2-degree of freedom system in the sense where the first mass is not moving at all. The process can be repeated with 3K upon M, okay? So you go through and you end up with this, again, so the M's cancel, we end up with 1 minus 3, which is minus 2. Okay, here we've got minus 1, here we've got 2 minus 3, so it's minus 1, and so on. Again, 2 equations, 3 unknowns. In your notes, that's 2 and 2. That's correct in your notes. Here it's wrong. Okay, so don't worry about that. And you go through and you find R22 and R32, and you end up with 1, -2, and 1. And that's where the two outer masses are moving in unison with each other, but the one in the middle is moving twice the distance, but in the opposite direction. Okay.